really. This is one.
Scroll down if you can open it up on your side as well, which will be helpful, I think. So we are, there are several reasons that we have to write the serial ones driver by ourselves. When I'm saying driver means we're writing the entire scene running behind the scene instead of just directly using the embedded function. And that function we have been using is, let me write it down here. So we have been doing this, right? Serial dot begin 9600. So that's the function available in the Arduino IDE. So it's already given to you, and you don't have to write whatever behind the scene. Actually, there are a bunch of registers need to be configured by this line. So they already did it for you. However, there are a couple of reasons. Whenever we reach that point, we'll be able to know why we have to write the driver ourselves. However, the conclusion is that first, you can't directly use this. No, remember it's a 0, 1. The Arduino IDE has a function like this, actually. Remember 0, 1 is being used where? For what? For RX, right? And for task 1 is 1200 bits per second. Task 2 and task 3 are 2400 bits per second. I'm just repeating myself, okay? Just make sure you know that. So for task 1, if you want to use serial 1, at the beginning you just directly do this, okay? It's gonna work. You can change it to 2400 to task 2, which is okay. But for task 3, we are not directly using this. However, we're writing the driver ourselves. It's called driver. It involves a lot of register configurations and enabling, disabling, all these kind of things. And so if you look at my website, all this information are given. I already told you how to do it. But you do need to know the registers that controls UART, okay? So not just for UR0, but also for UR1, 2, 3, okay? If there are 4 UR modules, so they all have to be configured before you want to use it. If you are not using the embedded function, okay? So you can see these registers, if you start from task 3, it's over here. These are the registers that need to be configured, and including the baud rate. And the baud rate, the register is 16 bits, okay? But only 12 bits are being used to define the baud rate. The reason for that is you don't really need a 16 bits. It's just too much, okay? And the higher 4 bits are unused. Look at this register structure here. So that's the register that stores the value to define the baud rate for that certain UR module, depending on what the N is, right? So for ours, it's UBRR1. UBRR1 is a register that defines the baud rate, and you store a value, just throw a value in there, and you can use this equation to calculate the baud rate. So see, baud is over here. We don't have any prescalers, so it's 16 mega, right? 16 mega divided by 16, you're actually getting 1 mega. And 1 mega divided by baud, minus 1, you're getting UBRRN, okay? And that value is that register, even though it only shows you UBRRN, however, that register represents 2 bytes. That's a 16-bit register, but 2 bytes. It's a 8-bit microcontroller, so you have to use 2 bytes to form that 16-bit register. So that register has a UBRR1H, UBRR1L. So H is a higher byte and L is a lower byte. Is that clear? Do you have a register and the name of the register exactly UBRR1? No. So UBRR1 has 2 bytes because UBRR1 is a 16 bits, right? So UBRR1 has a UBRR1L and UBRR1H, which is here. See? And the H is a higher byte and L is a lower byte. Why do we need 2 bytes? Because 8 bits or 1 byte is not enough to give you that all these different numbers of different baud rates. So we need more bits, but we don't need 16 bits exactly. So let's just use 12 bits. So the lower 4 bits of the UBRRH is used as the higher 4 bits of the 12 bits to define the baud rate. So there are totally 12 bits to define the baud rate. So the thing is, if you, for example, the calculation, you find out, so UBRR1, right? So this value should be, for example, 500, and that's a decimal number, okay? How could you assign this value to the 2 registers properly? A decimal number, you can convert it to a hex number. We don't know what that is, but it's going to be a hex number, which is fine. We can just totally just define it, right? And we can also assume that this guy is a 16 bits. Who cares? I mean, it just, if they don't have these many numbers, just to put zeros in front of it, right? If it defines this number 500 as a 16-bit number, it only probably occupies some bits here, but all the rest are just the ones, right? And in that case, doesn't matter what this number is. It's just a decimal number, but doesn't matter what that number is. If you convert it to a 16-bit format, and we should be ready to assign the 16 bits to UBRR1H and the UBRR1L, right? So this is what we need to do in the code. We have to do it. So how? So this number is over here, right? And these 4 bits over here stores the higher 4 bits of the 12-bit value. The value defines the baud rate. So we shift the whole thing by assume that there's something over here. Okay, there's something over here. They're all occupied by numbers. There are all numbers over there. Okay. I'm sorry, it's confusing, but there are all numbers over there. So if you want to assign values to this byte, you need to shift everything to the right by 8 bits, right? So these are out. And these are the 8 bits available, and then you directly assign these 8 bits to this register. Okay? And then for the lower 8 bits, what you want to do? You don't need to shift this guy at all. You just directly assign the 16 bits to this value because this is 8 bits. It's only 8 bits here, so they can only store the lower 8 bits. That's by the rule of the C language. Okay. This guy cannot host 16 bits. If you assign 16 bits number to it, can only store the lower 8 bits to it, which is what we want, right? So eventually you have these lower 8 bits, which is the value of this number. You store it over here for the at the lower 8 bits, and then the higher 8 bits are getting shifted to the right by 8 bits. So this digit over here becomes the LSB, and this byte can be stored in this register. That's how we do it. So that's for question number 2 in class number 9. I gave it to you probably on Monday, but didn't get a chance to finish it. So that is for number 2. Okay, that's how we do it.
For the high one, you shifted it to the right, and
Yeah.
then you're using the shifted bits, or
This. You shift it to the right by 8 bits, right? So that, like say, that's how we define that bulk value on use. Okay, so that number is a decimal number you assign to this register to this variable. You shift it to the right by 8 bits.
then wouldn't the first 8 bits be 0?
No, because these lower bytes will be shifted out. It's gone. If you shift all the 16 bits, so the first byte will be all zeros. Yes,
So
but it doesn't matter because when you assign a 16-bit number to a byte, it only takes the lower lower byte to be stored in the byte. You know what I mean? So the reason we want to do that is because we are hoping to assign this byte to this byte and this byte to this byte. That's the goal, right? So by shifting the whole thing to the right by 8 bits, you're able to move this byte to the lower byte. And so when you assign the whole 16-bit number to this byte, it will be able to store this byte in here. Okay, you can watch the video and try to see what's happening over here after the lecture if you're still not getting that. Okay, that's for number 2. And number 1 is already answered. I think that you can find the answer on the website. Number 3. So the vector for UART, and there's a pretty important concept to understand over here. So when we are doing UART receiving or UART reading, we do a serial dot read parentheses, right? And that one actually triggers an interrupt that you cannot see. It's running behind the scene. So it's being defined by that function and it's triggering a reading interrupt inside it. So since we are not using that serial.read function and we want to use an interrupt for reading, so which means whenever something is being sent to the air, remember the IR signals being sent to the air, and it's auto control, so that will hit that decoder and the decoder will output the bits to the data input, to the pin, to the RX, right? And then the RX will automatically take it in and store it in the buffer. And whenever something is being received by the buffer or by that receiving register inside the RX, it's going to trigger an interrupt. Okay, and then it's going to read it. So if we don't use the read function, it triggers the interrupt, and that value will be stored in that reading buffer, and we need to read it out. But however, interrupt will be triggered. Let me say this again. Okay, describe this again one more time. So when the IR signal, right, you press S and sending IR pulses as a light signal into the air. Is it still under control? No, it's in the air. There's no way you can grab it and stop it. And then it will be received by the decoder on the board. Okay? It's auto control. Okay? And the decoder receive it and will translate that signal into a UART signal since you programmed that way. Okay? With a certain baud rate. We'll start with what? It's a quiz question. It's a good time to give you a quiz. We are so used to in-class answers that it's open book, open notes. But now, what about Monday? Let's do a quiz. So, IR signal in the air, auto control, and the IR decoder receive it and will translate it into a signal. And that signal starts with what? A pull down. It's a start bit. Okay? And start bit, you have something follow the start bit. What is that? The data byte. And then stops at the stop bit, which is a pull up. So totally 10 bits. It will directly output. The output will be directly available from the decoder's output, and being sent out with a certain rate, and that's the baud rate that we defined, right? And that baud rate for task 1 and 2 for task 1 is 1200, and for 2 and 3 is 2400 that you can define. You have to find out the count by yourself. Easy. Okay? And then that one is out of control, so that pin, output of the decoder's pin is shorted to the RX of UR1. So that means RX of the UR1 will receive it and directly receive the data and put it into the buffer. This the register holds that byte. So that byte is being received by the reading register, and it's going to trigger an interrupt. Okay, it's going to trigger an interrupt and receive it. Probably trigger the interrupt first. Trigger the interrupt and then receive it, put the data into the buffer, and stop the interrupt. It will be triggered. The interrupt will be triggered. Okay? And so you don't have to. So my question is for you: do you need a timer to turn on the interrupt of the UART? Like we use the timers to turn on the interrupt, right? Do you need a timer to turn on UART interrupt, receiving interrupt? No, because whenever RX receives that pull down, it will start receiving it and will trigger the receiving interrupt. That's a very important concept to understand when you're coding it up. Okay? That interrupt is depends on if there's anything being received. So you are not using the timer to control it. But do you need a timer to control UART itself? But remember, we did use a timer to control something. But so what is that thing? Huh? Which SR? We use a timer to control timer 3, and timer 3 is being used for defining the baud rate. Remember? We turn on the pulses, then we directly turn on the timer, make a delay so its pulses last for that long, and then we turn it off, right? Then we turn off the PWM. We immediately turn on the timer for a certain period of time. Then we turn off the timer. So the timer 3 is used for defining the baud rate. Okay, but not the UART, not the UART. UR1, which is the RX we are using, that interrupt, that receiving interrupt, will be triggered whenever something's being received. It's not depending on the timer's overflow. All right. So for our task 3, it's different from task 1 and 2. Task 3, we need a UR1 receiving interrupt. And in that interrupt, we'll start receiving something. So I'm going to talk about the coding over there later. But for question number 3, you can see that for UR1's RX interrupt vector, there's a vector's name, and you can find it from the tutorial. Where is it? It is this one. So you can see, you can either use, there are 3 different vectors to be used, but we are only using the receiving interrupt vector. So which means that's a keyword for the ISR, right? So in the ISR, you have a parenthesis, you put a vector's name in it, so it's able to detect that name and enter that interrupt routine, okay? So it'll be USART1 underscore RX underscore vect, right? VECT. Follow that routine. For number 4, what is the baud value? If the desired baud rate is 2400 bits per second, so calculate this guy and you can use it for your code. You have to use this function to calculate it. I'll let you guys do it. It's 400 something, but that number is can be adjusted. If you are receiving a very weird data or errors, you can adjust it plus and minus something like 10, 5 to see if things are getting improved. Depending on the code, okay?
in the bottom?
Yes, over here. Yeah, 16 mega over here, and baud is over here. That's the value you are calculating.
What's the 16 and the?
Oh, the baud value is the value we know, the desired baud rate, which is 2400. And then you can calculate this number here, okay? And that number, remember, we'll assign it to the UBR1H and UBR1L, two registers. You need to use the shifting strategy, which is in question number 2. Any questions by far? What's up?
Can that number be a decimal?
Yes, it's a decimal.
What
That-
was the FOSC page?
It's a 16 megahertz.
Oh,
That's the frequency, major frequency. Any other questions? Feel free to ask. It's not a quiz. It's not.
In number 2,
Mhm.
you say if you declare baud value as a decimal number,
Mhm.
why can you assign it to an 8-bit register?
Yeah.
You're not actually assigning a decimal number into that register. It's converting it into binary,
Yes.
right?
Yes.
Okay.
Because that variable on the left hand side of the equation is 8-bit, right? So it's not able to take any. But the thing is, there's computers cannot store decimal numbers. Right? Eventually, they are converted to binaries, right? So since the ones on the left hand side is 8-bit, so eventually only 8 bits will be stored in there. If the decimal number, only the lower 8 bits of the decimal number is being stored in that variable,
Right.
but you have to convert it to hex first. Computer does it. Mm-hmm.
So you convert the decimal to text?
No, you don't. You just directly throw it in there. The IDE will be able to do it.
Okay.
Yeah.
As long as it's less than 255.
It could be 16 bits because a lot of times it will. But only the lower byte will be assigned to that byte variable.
Yeah.
Yes. So if you need to store the higher byte, you need to shift it to the right by 8 bits.
Mhm.
Otherwise, they will be tossed. Right?
Okay.
Yeah, I mean, it looks like a decimal number, but actually the computer sees it as a depending on the size, right?
Can you
It's
right shift a decimal number and
Yes.
it'll shift it as a binary equivalent?
yes, yeah.
Okay.
Uh-huh. So in your Arduino C IDE, you directly put a decimal number in there on the right hand side of the equation. It will be able to recognize it and create a certain space for it depending on the value. Right? So if it's larger than 8 bits, it will be able to find a 16-bit space for it. So this is something we don't have to worry about. Yeah. Any other questions? Number 5. So it's asking to calculate the number of counts, right? The counts to form 2400. And do you have any question on that? Timer 3, right? Timer 3 to do that. So it's going to be 1 over 2400 to find out the time. And for the time, you times 60 mega. Find out the counts, okay? Now let's look at number 10. Wait, finish everything in number 9? Almost. Yes, we do. Yes, we do, right? Okay.
Can you repeat number 5 again?
Number 5. Number 5 is the duration for the bits, right? For the bits. Because the bit rate, the baud rate is 2400 per second. So you can find out the time duration per bit. If you know the time duration per bit, you know the counts, right? PWM. So be this, this, right? And we desire this to be 1 over 200, 2400 second. Okay, so for timer 3, you can easily find out the time for this duration to create a time delay using timer 3. Okay. For UART registers configuration, there are a couple of others. I'm not asking you guys to explore it, so I'm directly giving that to you guys. You can see you need to define RxCIE, RxEN. So RxEN enables it, RxCIE enables the interrupt of the receiving. You can see these bits are over here. And for UCSRNC, that's a UART control and status register, and we need to configure these 2 bits. It's a UCSZN220, right? 3 bits. That defines the size of the bit, size of the data. So it knows that between the start bit and stop bit, right? So the 2 bits, how many bits are in there for the data as a data, right? So if you do a 1-1, which is number 3, for these 3 bits, you are defining a 8-bit data size for UART, and that's usually what we use. So for UART, it's usually just a byte, just byte by byte, okay? So here's a configuration for that. It's given. You don't have to modify it. It's given. Just directly use it. All right? So you can see these 2 bits are being asserted, and these are also being asserted. And for these 2 registers. Okay? And that's how you give the belt value. You calculate the belt value. It could be a decimal number. Okay? That's how you assign the lower byte and higher bytes to these 2 registers.
There was a 16, but since there's no pre-scaler, what's the 16 for?
It's just have to ask the digital designer of the chip, I think, but we just follow the equation. Okay, yeah. For in clocks number 10, question number 1, what is the data type of the transmit checksum variable, and what is the maximum value it can store, and what if the value overflows? So this is something about the task 3's template. Let's scroll down over here and look at it. Okay. So after you upload the code to the microcontroller, the first step is press the M. So the M will let the user to type the message to it. If you forgot how that works, I can show you one more time. Do you need that? No? What about the rest of class? Do you need to remind yourself about this one time? So whatever happened over here is basically I type the string.
So you
press M first.
Lowercase m first to enter.
So see here, you press M and it asks you to type something in there, okay? And one more thing is a little bit trickier is it's different from what we have been doing with the Arduino serial monitor. This one, when you type it, it prints it. So you have to program it in there. See, if I type
string, so let's type hello.
See, when I type it, it prints it. It's not doing this automatically. It's basically when you type it, it's being sent to the microcontroller, and the microcontroller printed it back. So you have been using the Windows or any other operating system of the laptops for so much, you are assuming this should be, granted, right? This should be, like that automatically. Actually, it's not. So you have to program into a microcontroller to make that happen. So you type something, you send it over, and then it prints it back. All right.
World first. Yeah.
And then after I'm done with the typing, I press S. Okay, I press S. So I press S, that pressing event will turn on a flag, okay? So which means a transmission, you can name whatever you want. So if I press it, its transmission becomes true, okay? Transmission of the string becomes true. And then the interrupts, the idle state will detect that flag and just keep moving forward. All right, you're not dealing with the transmission in the S case. The S case only turn on the flag. Keep in mind. And then because you turn on the flag, the ISR will handle that and keep sending things over. Okay, so there will be something in the air and being sent. So it's auto control, right? And the decoder will receive it. So how to control the RX ISR? Do you need a timer? Need a timer for the receiving? No. Because of what? Because UART directly interrupts whenever something's getting received. So that's how things works. You press S, it turns on the flag, and the ISR, one of the ISR, the transmission ISR, will start sending all these bits, the data, with the message, one by one. Okay? One by one, you will need a little index over there to get incremented one by one. So it's able to send one by one from a transmission buffer. So, and just one byte by one byte. So you got that byte by byte being sent. It's actually a lot of data. You know, this every single character has 10 bits. Okay? Keep in mind, for UART, every byte deserves a start and stop bit. It's not like you have one start and one stop at the end. No. There's like one start, one stop for each byte. So in that case, I type hello world over here, right? And if I press S, the transmission interrupt will start, put so much effort sending everything over, right? So it's gonna, like a lot of light pulses, you couldn't see, but a lot of light pulses in the air, eventually being received by, keep in mind, all these data bytes in the air, they are being wrapped by the start and stop bits. Keep in mind, keep that in mind. Okay? It's a lot of packages, right? 10 bits, 10 bits, 10 bits. But every byte starts with the start bit and stops at the stop bit. So whenever these packages are in the air and your decoder starts receiving it, so the first bit of the first byte, which is the start bit, put it down, will be detected by the receiving ISR, and that receiving ISR will trigger that receiving interrupt, and will start taking in the first byte and being stored in your receiving. Okay? And then you immediately read it out because the receiving buffer doesn't have too much space. Let's say just probably one byte over there. Okay? That just behind the RX pin. Okay, there's a little byte taking in that byte being received. Let's see if you really see that byte somewhere. Just looking at it. Oh, it's that byte. So got that byte being received. That's right behind the RX pin, right? There's a little byte receiving that thing from the air. Okay? You receive one, you want to put it into a receiving buffer immediately, and you increment your index. So it's ready to take another one. You don't have much space for that buffer, for that byte right behind the RX pin. Keep in mind, you're just one byte over there. There might be 2 bytes sometimes, but no more than that. Okay? So whenever that one is being filled up, receiving interrupt is being triggered, you have to read it out. You have to read it in order to clear up that interrupt, so it's able to receive another one. Otherwise, all these bytes are in the air and they are taking a line. There will be a traffic conflict, right? So it's trying to get into the buffer, get into the RX pin, and you won't be able to figure it out. You are losing data. Okay, you are losing data. So whenever the first byte is being received by the RX pin, it triggers that receiving interrupt. You want to read it out immediately, okay? Just read it immediately, and then you will be able to take in another one and being stored in that little byte right behind the RX pin. And then you immediately read it out and put it into another array. Okay? Because it's being labeled or being wrapped by the start and stop bit, so your UART can always detect it and trigger the interrupt. That's how the interrupt is being triggered, because it detects the stop and start bit. So it's getting triggered. Okay, it's getting triggered. Any questions on this? That's how it works. Okay, that's how it works. You have to know how it works first in order to program it. If you don't even know this, there's no way that I can program it. That's how the hardware works. Okay. So see here, I typed it. It will be saved in array. Okay, it's called a transmission array, transmitter array, whatever. I forgot the name. Okay, and that's the array being stored in the microcontroller. And then whenever the interrupt, you press S, that flag is turned on, and the ISR will start sending byte in that array, because you store this in the array when you type it in M. Okay, we'll send it byte in that array, and that will go to the air and then trigger the interrupt, and then the receiving interrupt will take it in and read it and put it into the receiving array. Okay. Any question on this? Am I losing anybody? Everybody? Questions? So boring without a quiz? Any questions? You can ask any questions, since I can tell you 80% of you guys are not getting it, if I'm right.
So the max buffer size that we're looking at, that's 32 entries into an array of bytes.
Yes, 32 bytes in there. That's what we defined, but you can make it larger, which is fine.
Okay.
But we just put a 32 over there as just one example.
But each one of those numbers is like 1 byte. Whatever you set that, if you set it to 64, you'd have 64 bytes.
Yes.
Okay.
Yeah. Other questions? Could be very fundamental.
Can you write it out? Like, can you know the process?
Okay.
It's kind
Cool.
of hard to understand.
Sure. Yeah.
Using your hands.
Yeah. So here's the ISR for sending. It's a pseudocode, okay? And ISR for receiving. And I press S. I press S. There's a transmit buffer. A transmit buffer with multiple characters that you previously stored in there. Okay, well, you're taking this out and no, you press S, not this one, sorry. You press S, transmit flag becomes true, okay? So in sending, you have idle state if transmit flag is true, you start doing the sending thing, okay? Start doing the sending thing, or jumping to different states. So whenever you do this, the IR pulses. Whenever you press this one, right? You press this one, it becomes true. And in your ISR sending, you are doing the PWM, right? PWM, you turn it on and off, depending on the bits. And things will go to the air, right? So we put down first and put up eventually. That's the start bit. The stop bit. It's gonna be in the air. And then the decoder here, right? The decoder has 3 pins. And what's the pin number here? 44? I forgot. Or 19, I forgot. Doesn't matter. So this one decoder will receive it, okay, and convert it to the UART protocol. You put it down first, right? and then pull up. And that's being received by the RX pin of the UR1 module. And you receive it because every time it detects that pull down activity or event, it will trigger this receiving interrupt. So you immediately read it. I think that register's name is here. Template is very helpful. The register's name is UDR1. That's a little register, UDR1. That's the register's name. As the register stores whatever is being received temporarily in here. If something's being received, it will be placed in here, and the receiving interrupt will be triggered. Okay, so that's why so in here you can read it in here because this will be triggered. So you come into here, you read it. You have to put this guy on the right hand side of the equation to read it. So give this one to receiving buffer with the index over there. Okay? And then when you are done for the receiving, you do a I plus 1. So next time you receive another one, triggers this one again, which means it's another byte being received, and you want to read this guy again, but I will be incremented by 1. So eventually you store everything, all the data in this receiving buffer with the index I. So every location in the array is storing 1 byte. That's the whole process. But for the details, I will talk about that as well. But that's the whole process, the workflow. Okay? So when you press R, are you start with, is it going to receive? So there's a case R as well, right? Case R. Case R. Question, very simple question. Are these cases in the SRs or somewhere else? Are these in the SRs or is it somewhere else? They're in the loop. Your ISRs are interrupting the loop. Okay? So these are in the loop. So who is detecting this? Who is what is being used for these ones? Where are you getting these cases? Where are you getting these cases? These cases. The commands. So where command is being sent to? What is receiving the commands? UR0 from the USB. So you are doing a serial dot read, okay, for the command, right? So when command is detecting that, it's a totally separate module, okay? So it's getting into different entries and then do certain things. When you press R to receive it, okay? We press R to receive it. Is the microcontroller starts receiving data, we'll press R. Okay, other people also think about it. If you press R, is the microcontroller starts. Let's do a quiz. Quiz number 10. I'm kidding. So we'll press R. It's like, I just did a quiz. I have another quiz after this, please. So when you press R, is the microcontroller starts receiving when you press R? Think about it. Yes or no? Yes, why? No, why?
Waits for receive new message to be true.
Actually, yes. Do we have other answers from anyone else? Remember, you press S. The flag is true. It's in the air. It's out of control. And that's first bytes. The first bit of the first bytes pulls it down will trigger what?
It'll trigger UR1.
Will trigger UR1's receiving interrupt.
So it'll be in a buffer.
It's in the buffer. And do you need to press R to receive it?
No. Just
Who is receiving it? How do you receive it? The receiving SR. Receive it. And put it in where? Here. So when you press S, the data is in. The data is already in there. Okay? It's happening really quickly. You press S, done. So when you press R, what's happening?
It's just reading the
It's
buffer.
reading, it's printing. It's reading, it's printing from this guy. That's it. Make sense? Okay? Any other questions on this? Let's move forward. Let's record it. Always come back to watch the video. It's always available. Question number 2. Oh, this is something we know, right? So remember I told you guys if you are not using SR, you need that long, like 4 lines to turn on the PWM. If you are using SR, it's simplified. So you don't have to, reconfigure all the registers. You just need 2 lines. You just need these 2 lines. Which 2 lines? You just need. I don't have it here. Okay, I'm gonna write it down for you. TCCR5A or 1 COM 5B1. First line, second line, OCR5B. Or LED on. So what is in LED on? What is that?
This is low.
That's the duty value, right? Wait, low, yeah, it's 0. No.
What?
No, we're turning on the PWM. Turning on the PWM, so LED on should be the duty number. The duty number being put in this register will give you that duty cycle, right?
Wait, is that CO?
OCR5B.
On the first one.
COM 5B1.
Okay.
Okay, so you can use this for the code.
The number is 255.
255. Which one? Oh, the first one.
That's the duty number for LED on.
Yeah. So what we are doing here is, any question on question 2? That's the answer. Okay. For you are saying LD. No, it's not 255. I was thinking you are asking for the first question. No, it's not.
1/38K.
1/30 times 10%,
Yeah.
right? Because 1/38K is
times 16 megahertz times 10%.
no 1/38K will be the period of the PWM, right? And for the OCR5B is storing duty value, which is 10% of it.
But it's a
No, it's a
seconds
count.
or counts?
It's a count. So you have to use 1/38K
times
times 60 mega and then times 10%.
Yeah.
Yeah. Okay, so for question number 1, we are making a fake address for it. So which means you can look at this. This is the whole message. And the message is not necessary to be that long. We have a maximum length to be 32 bytes in there. But we don't usually use all of them. If you just type hello world, it's not actually 32 bytes in there. So each block is 1 byte. And because some of the communication protocols require address, address for the registers to make configurations. However, for this simple application, we don't need address. But I'm trying to place a fake address in front of the data byte, just let you know how to deal with it in the future. Okay? So for the whole message, actually we have a source address, a destination address. These are just constants. It's given. You can do whatever you want. But what I did is here is source address is 1, just number 1, and destination address is number 255. You can change it to whatever, as long as it's within 8 bits. It's just some constants you plug in front of the real data message. And remember, every byte is 10 bits, okay? Even though it's an address, but still have start and stop bits. It's 10 bits, okay? So each single thing is 10 bits. And followed by your message, like if it's hello world, that'll be the ASCII code for the hello world over here. And then stopped by a null, null, which is /0, that's a character, which is recognized as a terminator, as a string. That's very important. You will be able to tell. But now let's keep in mind, whenever you are sending a message with a series of characters, which is a string, you need to end it with a null, okay? It's a /0. You just have to type it /0 in there as a character to be sent. It will be recognized as null, okay? The end of the string. And followed by that will be the transmission checksum. So the checksum is the error checking mechanism we are putting in this message. And the checksum is the addition or summation of all these characters being sent, but not including the null and the checksum itself, not including the null, okay? So it's basically all the ASCII code of the source address, destination address, all the messages as well. All these bytes being added together, their ASCII code being added together. So in your C code, you can just simply using like character A plus character C, right? If these are the two characters you're sending, and the characters being added together, they're actually getting their ASCII code being added onto each other. So eventually, when you are sending it, after you put all the messages into the message block, you immediately, before you send it, you immediately calculate the summation of the ASCII code of every single character. And that number is being used as another byte to be sent, and you send it over, and whenever the receiver receive it, it will definitely take in all these bytes, all the data bytes into it, and store it, but also will, at the receiver's end, we'll do a checksum as well. So we'll add all these characters together as well, and then compare with whatever is being sent as the checksum from the transmitter. Any question on this?
Yeah, so for the maximum value, it'd be 27 bits.
You look
bits in.
look at that one. So that one, if you look at the template, let me see.
Because if you're like looking at
Yeah.
the source address, destination register, so you can't send data with those 2 bytes.
Yeah, they're all bytes, right?
Yeah. And then you can't send it with the 0 or the 31. So then you're left over with the 27.
No, these are bytes, not bits, right?
Oh, sorry,
So
bytes. You're
yeah,
looking at the 27 bytes to send.
28.
20.
No, but that's not the answer, right? For question number 1. So what is the data type of the transmit checksum? So the transmit checksum is just a byte, right? So it's going to be unsigned integer 8. Because you can see it from the template, it shows you over there. So that's the first answer for that. And second one, what is the maximum value it can store? So for a byte, it can store 255, right? But the thing is, if you have a lot of characters and you add all these characters, ASCII code value, usually they are like 35 or something, right? So these values to it, eventually it may exceed 255. So what's going to happen after that? You're over to 0, right? And then start from 0 again. We don't worry about that, because even though it's roll over, we can still check they're the same, right? The sending one, transmitted one, and received one, if they roll over at the same time. So we can always just check the result, which is fine. Question number 3. What are the first 2 bytes stored in the message? Source address and destination address shows you in the diagram over here, right? This guy. And what are the last 2 bytes? which is question number 7.
The null character and then transmit checksum.
Mm-hmm. If you add 2 characters, what are they actually being added together?
The ASCII code.
Yeah. What key creates the /R character?
Is that control?
Yeah. No.
Or is it
Enter.
enter?
Enter key. Enter key. Remember when typing in the M, when I press M, it let the user to type your message, and then you press enter, it creates that /R character, and your code will detect it and send it and enter it into the transmission buffer. So that's something being used as a condition, right? If something like a /R is being received, then do something. Okay. Number 6. It's just the syntax of the C code. Okay. So you are assigning a CMD a command to that transmission buffer. It will be stored at location 2. Okay, I'm talking about question number 6. Okay, it will be stored at index 2. However, there's a ++, not something here. It's on the paper. Okay, on the paper. Question number 6. Okay, so for that one, do you see a transmit buffer bracket I++ over there? Yeah. So that one will assign CMD to location 2, index 2, and then after that assignment, it will add a 1 to I. So I eventually becomes, yeah. Just keep in mind, after that line, I will be incremented by 1. And for question number 8, we'll work on it on Monday, since we don't have time. But you guys have to work pretty hard, I think, for task 1 and 2. So see if you can get it done before the end of Monday. Okay.
What would the quiz be on Monday? Like which lectures?
Quiz for what? For the course? I don't think there's a quiz. Do we have a quiz?
You're just joking.
Yeah, I was joking. You just have a trauma. Your trauma is too deep. Oh, turn it in on Monday. Not today. Oh, but number 9, yes. Thanks. Yeah.
My brain just makes me stress mode.
Can I turn in my class 9 later to you today?
Why? I forgot, but you should put on the copy though.
Yeah.
Might be fun this time. Okay.
Okay. So will you be available after 2:30?
I stayed for 4 hours.
Or cause
No, I'll be gone, I think. Send it by email.
What's your grade now?
There's only one.
You were arguing that goes. That's gonna be rushing from like wait for my comeback and exam.
I will go get that. I'm so sorry.
Yeah, you
Go
do.
get that later. And then I'll do it. How long is it?
I'm gonna be here till like 5 or 6.
Okay.
Yeah, it's okay. I forgot to text you, bro. It's all good. I was gonna text you from my team. You're good, bro. Don't worry. It's okay. not good, no.
Like, I wanna talk to you.
Is it gonna like,
Yeah, and I
okay, wait,
like,
what do you need done?
but like now.
I was I'm walking through your.
Oh, cool, you can use the, any of the other.
And I'm crazy to like.
Use the hack roll as a background table.
They're on the desk.
Yeah, that's fine.